Hello, welcome to another lesson. Today we are going to study how to use the Hamiltonian formalism and the Hamilton-Jacobi formalism into some topics of electrostatics. We are going to work with the dipole in this case, and recall that this is a very famous concept in electrostatics. Let's say that, for example, we have two electric charges that, let's say that this is minus q and this is q, and they are separated by a distance, let's say d. The important thing here is that these charges are going to be under the influence of an electric field that is going to be constant. We are going to name it as E. We are going to put the center of the coordinate system here. So we will say that this distance is d over 2. Okay, and we are going to be interested in calculating what is the potential energy of the whole system that we have here. Looking that, these charges are under the influence of an electric field. This electric field is going to make this system to feel a torque. Okay, I mean, these electric charges are going to start moving due to the influence of the electric field. Actually, looking that this charge is positive, it will be moving to this direction and this other one to this direction until they become in this position. Okay, so this dipole is going to have a torque. So remember that the equation to calculate a torque is r cross f, that r is the vector that points from the center of the coordinate system to the center of the particle. This will be r, for example. But we are going to have two torques, one for each charge. So let's say that the magnitude of the first torque is going to be given by, the distance r, which is going to be d divided by 2 times the force F, and the sine of theta, which is the angle between r and F. Remember, if you have a cross product of A cross B, for example, this is AB sine of the angle between the two vectors. So it is easy to see that actually the torque that is going to feel the other particle is going to be exactly the same. Okay, so that means that the total torque, which is going to be the sum of the two torques, is dF sine theta. And also, you know that we can express what is the magnitude of the force F in terms of the electric field as Q times E. So the torque is equal to d Q E sine theta, where we can easily see that this Q times D is the very well-known concept of dipole moment, P. So we will see this as P times E times the sine of theta. Okay, another famous equation is that, you know that to calculate the work of a force, you make this integral F dot dl on a trajectory z. You know that if you have a force acting on an object that is moving on a trajectory c, we will have a work made on this object equal to this integral over here. For example, we can locate the differential L like here, but we are here in a motion, a circular motion. This dipole is in circular motion, so the equivalent equation for this kind of motion is that we are going to get the integral of the torque d theta from an initial angle theta to a final angle theta. Okay, perfect. So this is how we are going to calculate the torque. This means that the torque is going to be equal to the integral from theta 0 to theta f of P E sine theta d theta, which immediately we see that this is P E cosine theta from theta 0 to theta f. And let me recall that in this case, looking that the motion is going to be in this direction, the final position of the dipole charges are, well, it's going to be the vertical one, where the angle theta is 90 degrees. So that means that this final angle is pi divided by 2, and this leads us to minus pe cosine of theta 0. So yeah, due to the fundamental theorem of calculus, we get this minus sign, remember. So we can say that the work is equal to minus pe cosine of theta 0. And also remember that we usually define the work as minus the change in the potential energy, that we are just going to call it as U. And yeah, this is because, well, we're actually interested in finding what is this potential energy. Remember, so this means that U is going to be equal to P E cosine of, let's just say theta. And something that we can do here is to express this as P and the electric field, which remember that is Q divided by 4 pi epsilon 0 r squared, and then cosine theta. So if we consider this thing that we have here as some constant k, we will get that the potential energy is going to be equal to k cosine theta divided by r squared. So this will be the potential energy associated to this mechanical system, in this case an electrical system. Okay, perfect. So the reason why we calculated the potential energy is that, well, we need to find what is the Hamiltonian of the dipole. So we still need to find the kinetic energy. But remember, well, actually on the first videos of the channel, we made a lesson to explain how to get the kinetic energy from Cartesian coordinates to spherical coordinates of a general Lagrangian. So that is that we showed that the kinetic energy, that is 1/2 mr dot squared in spherical coordinates, can be written as the next equation. Okay, and this is the kinetic energy that corresponds to spherical coordinates. And with this we can say that the Lagrangian is the kinetic energy minus the potential energy. So it will be this expression and then minus k cosine theta divided by r squared, where this is the Lagrangian of the electric dipole. Okay, so what we need to do now is to find the Hamiltonian of the dipole, but we know that the Hamiltonian can be seen as, it will be phi dot, the derivative of the Lagrangian with respect to phi dot, plus theta dot, the derivative of the Lagrangian with respect to theta dot, plus and r dot, the derivative of the Lagrangian with respect to r dot, minus the Lagrangian. Okay, where remember that we define some quantities named as conjugate momentas, as pi equals the derivative of the Lagrangian with respect to qi dot. So for example, p phi will be the derivative of the Lagrangian with respect to phi dot. Okay, so we need to find those quantities. First of all, p phi will be, what will that be? It is mr squared sine squared theta phi dot, taking the derivative of this Lagrangian, of course. Then p theta will be mr squared theta dot, and then pr will be just mr dot. Okay, with this, remember that we need to solve these equations for the dot variables. So phi dot is going to be p phi divided by mr squared sine squared theta. Then theta dot is p theta divided by mr squared, and r dot is pr divided by m. So we need to take this into the Hamiltonian definition. So we will get that H is equal to phi dot, which is p phi, and recall that this quantity is p phi, so we will get a p phi squared here, and then divide it by mr squared sine squared theta, plus again we will have p theta squared divided by mr squared, and then plus r dots, which is pr, that will be squared divided by m, and then minus l, but l is the Lagrangian, so it will be minus this quantity, so that will be m divided by 2 r dot squared minus m divided by 2 r squared theta dot squared minus m divided by 2 r squared phi dot squared sine squared theta, and then plus k cosine theta divided by r squared, of course. Perfect. So what is this going to be? Well, as you can see, we need to change these r dot, theta dot, and phi dot to the p variables. So we will get here the same thing for this expression. And for this, we will get minus m divided by 2 r dot squared, but that is pr squared divided by m squared. Then minus m divided by 2 r squared theta dot squared, but that is p theta squared divided by m r squared squared, minus m divided by 2 r squared, let's say sine squared theta, and pi dot squared, but that is p phi squared divided by m r squared sine squared theta squared, and then plus k cosine theta divided by r squared. Okay, and this is the magic of the Hamiltonian formalism. We can erase the derivatives with respect to time of the generalized coordinates in terms of some new variables p. Okay, so if we keep simplifying, we will get that the Hamiltonian is, as you can see, we can cancel this mr squared with this squared, this mr squared sine squared with this, and that also happens here with this m. So we will get p phi squared divided by mr squared sine squared theta. With this, we will get, a p phi squared divided by 2mr squared sine squared theta, plus now this one with this one, we will get something like this, p theta squared 2mr squared, and then plus, well, something similar, right? pr squared divided by 2m. Okay, and then plus k cosine theta divided by r squared. Okay, we can take a factor of 1 divided by 2m here to multiply p phi squared divided by r squared sine squared theta plus p theta squared r squared here plus pr squared plus k cosine theta divided by r squared. Perfect. So with this we have found the Hamiltonian function for the dipole that we mentioned at the beginning of the lesson. This is the Hamiltonian associated to that electric system. Okay, so to find the equation of motion of this, we're going to introduce the Hamilton-Jacobi formalism that we have been studying in recent videos. Recall that the Hamilton-Jacobi equation for a Hamiltonian H that depends on Qi, Pi, and T, it's that we have this Hamiltonian, but now evaluated at the S, well, the partial of S with respect to Qi and the time, plus the partial of S with respect to time equals to 0. In this case, again, we have a Hamiltonian that it does not depend on time. So we are going to construct the Hamilton-Jacobi equation as the next. It will be 1 divided by 2m, that multiplies 1 divided by r squared sine squared theta times the derivative of s with respect to phi squared. Yeah, that corresponds to this, p phi. Then plus 1 divided by r squared, the derivative of s with respect to r squared, plus the derivative of s, sorry, here it's theta because we have p theta here. Okay, so here is the derivative of s with respect to r squared, and then plus k cosine theta divided by r squared, plus the derivative of s with respect to time equals to 0. Okay, this is the Hamilton-Jacobi equation for an electric dipole. So what I want you to notice in the Hamiltonian expression is that we do not have an explicit dependence on phi and t. Okay, it only depends on r and theta, but not in phi and t. So that means that we can propose a solution for the Hamilton-Jacobi equation that is going to be of the form a of r plus b of theta plus z, actually it will be plus p2 phi minus p1 t. Okay, recall, looking that phi and t do not appear in the Hamiltonian, we can express this in the method of separation of variables. We can express the functions that depend on phi and t just as linear functions. We have been using this strategy in some other examples in the study of the Hamilton-Jacobi equation, and in particular when we use this method of separation of variables. So we make this proposal for the solution. So this allows us to say that the derivative of s with respect to phi is equal to p2. The derivative of s with respect to theta is equal to the derivative of v with respect to theta. The derivative of s with respect to r is going to be the derivative of a with respect to r, and the derivative of s with respect to time is equal to minus p1. So we are going to substitute those values into the Hamilton-Jacobi equation to get that 1 divided by 2m multiplies 1 divided by r squared sine squared theta times p2 squared plus 1 divided by r squared times the derivative of v with respect to theta squared plus the derivative of a with respect to r squared, and then plus k cosine theta divided by r squared equals to minus the partial of s with respect to time, but that will be minus p1, so we will get p1 here. Okay, perfect. So we are going to multiply all this equation by the factor 2mr squared, and we are going to get p2 squared divided by sine squared theta plus we will get 2m, the derivative of v with respect to theta squared. Actually, no, this will be alone, right? Yeah. So here we will get it will be r squared, the derivative of a with respect to r squared, plus 2mr squared, that cancels with this one, so it will be 2mk cosine theta equals 2mr squared p1. So with this, we are going to put in the left-hand side of the equation the variables of r, and in the right-hand side everything that depends on theta. So we are going to get r squared, the derivative of a with respect to r squared, minus 2mr squared p1 equals, let's say this will be a constant. Well, No, let me make the let me write the variables that depend on theta here. So it would be minus the derivative of v with respect to theta squared minus 2mk cosine theta, and then minus p2 squared divided by sine squared theta. So we are going to establish that this is going to be equal to minus p3. So we will get that the derivative of v with respect to theta is squared plus 2mk cosine theta plus p2 squared divided by sine squared theta is going to be p3, and we will get that 2m r squared p1 minus r squared, the derivative of a with respect to r squared is going to be equal to p3. Okay, so as you can see, we have an equation here, a differential equation that is with the independent variable theta, and for the other one the independent variable is r. Okay, so we can solve these equations to get b and a in terms of their variables. So for example, for the first equation, we will get that the derivative of v with respect to theta squared is going to be p3 minus p2 squared sine squared theta dividing minus 2mk cosine theta, and well, we can take plus minus the square root of this to cancel this, and then with this you can easily see that b is going to be the integral. Let's take the solution for the plus sign only, just for convenience. It will be the integral of the square root of p3 minus p2 squared divided by sine squared theta minus 2mk cosine theta d theta. Perfect, so that will be b as a function of theta. Then we will get that, what are we going to get? Well, we will have 2mp1 minus p3 divided by r squared equals the derivative of a with respect to r squared, okay, just by taking these to the right hand side and then dividing by r on both sides. So, and taking this p3 to the other side, of course. So we will get that a can be seen as, again, we are going to take just the plus sign solution to get that this is the square root, the integral of the square root of 2mp1 minus p3 divided by r squared dr here. Okay, perfect. So with this a and b, we can construct the solution for the Hamilton-Jacobi equation for the dipole. So it will be a, which is this thing, plus b, which is this thing over here. And then remember that we said there was a p2 phi and minus p1t. Perfect. This will be the function s that solves the Hamilton-Jacobi equation for the dipole. And again, remember, this s is representing a canonical transformation because this s is a generating function of a canonical transformation. So this means that s needs to verify the equations pi equals the derivative of s with respect to qi, and that qi is equal to the derivative of s with respect to pi. So in this case, these are the little p's. So for example, p1, p2, and p3, they will represent, well, pr, p theta, and p phi. Okay, so this is for pr, p theta, and p phi. So this means that, well, pr is going to be the derivative of s with respect to r, p theta is going to be the derivative of s with respect to theta, and p phi is going to be the derivative of s with respect to phi. Okay, perfect. So, as you can easily see, P phi is equal to P2 because we are taking the derivative with respect to phi of all this, but the only element that depends on phi is this. So we can see easily that P2 is equal to P phi. And let me change this letter for a little p just for not to get confused. Okay, then PR is going to be the derivative of S with respect to R, but these whole elements do not depend on R, so that means that we only need to take the derivative with respect to R of this. But look that we have an integral with respect to R, so we immediately see that PR is going to be the thing that is inside that integral, which is this thing that I'm writing here. Perfect. So this is PR. And something similar is going to happen with the theta variable. So with the same reason, this is going to be the square root of P3 minus P2 squared divided by sine squared theta minus 2mk cosine theta. Okay? Perfect. Okay. So what other thing can we do? Well, we can use this formula that we have here to find the Q's, the upper Q's, that are going to tell us what is the canonical transformation generated from S. So, for example, Q1 will be the derivative of S with respect to P1. So that will be, well, look that only two elements depend on P1 in this S. So we may need to take the first minus t term here, and then plus the integral of the derivative with respect to P1 of the square root of 2m P1 minus P3 divided by r squared dr. Okay, perfect. So if we make this calculation, here we will get minus t plus the integral of 1/2 2m P1 minus P3 divided by r squared to the negative 1/2 times 2m dr. We can cancel these 2's to get that Q1 is equal to minus t plus m times the integral of dr divided by the square root of 2m P1 minus P3 divided by r squared. Perfect. This will be the Q1 that, remember, is an element of the canonical transformation related to S. Sorry. So Q2 is going to be the partial of S with respect to P2. So let's see what elements depend on P2. Well, this element depends on P2 and this other one too. So we are going to take the derivative with respect to P2 to get phi plus the integral of the derivative with respect to P2 of, well, let me copy this element. Okay. Okay, so we will get phi plus the integral of 1/2 P3 minus P2 squared sine squared theta minus 2mk cosine theta to the negative 1/2 times minus 2p2 divided by sine squared theta d theta, and this leads us to Q2 equal to phi minus, these two can cancel with this, and then the integral of p2 d theta divided by sine squared theta, the square root of p3 minus p2 squared sine squared theta minus 2mk cosine theta. Okay, perfect. So this will be Q2. Okay. Okay, perfect. So we go with Q3. That will be the derivative of S with respect to P3. So what will that be? Well, if we see, we are going to have to take the derivative in this piece and then in this piece because they have a P3. So we will get the integral of the derivative with respect to P3 of the square root of 2mp1 minus P3 divided by r squared dr, and then plus the integral of the derivative with respect to P3, and let me copy this quantity. Okay, we will get this. So Q3 is going to be the integral of 1/2 2mp1 minus P3 divided by r squared to the negative 1/2, and then minus 1 divided by r squared dr, plus the integral of 1/2 P3 minus P2 squared divided by sine squared theta minus 2mk cosine theta to the negative 1/2, and then the theta. Okay, perfect. So this will be, well, we will get that Q3 is equal to minus 1/2 the integral of dr divided by r squared square root of 2mp1 minus P3 divided by r squared, and then plus 1/2 the integral of d theta divided by the square root of P3 minus P2 squared sine squared theta dividing minus 2mk cosine theta. Okay, perfect. So this will be the equation that defines the Q3 variable, the upper Q3. So to be able to find an equation of motion in the spherical coordinates, we are going to use this equation that we found for Q1. So let me write it here. Q1 is equal to minus t plus m, the integral of dr divided by the square root of 2m, what is happening, 2mp1, and then minus P3 divided by r squared. So what we are going to do here is, first of all, let me write this as Q1 plus T equals M times all this. And then we are going to take the derivative with respect to R on both sides. So looking that this Q1 is a constant, is going to be 0. So we will get the derivative of T with respect to R is going to be M times the derivative with respect to R of this integral that is with respect to R. So it's easy to see that, well, looking that they are, well, we are taking the derivative of an integral of R. This can be seen as the derivative of T with respect to R equals to M times 1 divided by the square root of 2mp1 minus P3 divided by R squared. And this is equivalent to the next equation. The derivative of R with respect to time, which is R dot, is equal to the square root of 2mp1 minus P3 divided by R squared, all divided by M. So as you can see, we have a function of R, well, the derivative of R with respect to time. Okay, so if you want to find R of t, you just may need to integrate this function that we have here with respect to time. Of course, if you do that, you need to separate variables. You will get something like this: dr divided by this square root to mp1 minus p3 divided by r squared equals to dt divided by m. So with this relation, taking the integral on both sides, you are able to get that function r of t. Okay, perfect. So for now we are going to stop here. This will be the final important result of the lesson. And recall that r of t is a function that tells us the position of the electric charges that compose the dipole, the electric dipole that we are dealing with right now. So yeah, a function r in terms of the time. Perfect. So I think this was a good way to introduce the Hamiltonian formalism with something in electrostatics.